It's a pleasure to be here again. Right, I would like to begin with some motivating goal. Even though I see myself mostly as a complex geometry, sometimes it's fun to do something else. So the goal is take a global function field and then aim to construct a geometrically simply connected surface Y of general type such that k rational points exist, but such that we have a vibration from the surface. Pardon?
Y is the surface of.
Oh, yes, yes, yes. Everything is over k. A vibration from Y to P1 such that if I take the rational points and I look at the image set in P1, then this is finite. Right. Why is this interesting? I think this is interesting. Someone correct me. We believe that this might be the first simply connected example of a surface over a global field where you can actually prove the Brauer-Manin, the Bombier-Relin conjecture. So this is first example, I should say simply connected example of a surface where one can prove Bombier-Relin. It's known for subvarieties of abelian varieties, but then that's never connected. So here, hopefully, we're going to see an example that's of a novel kind. There are examples, I should say, exist even over number fields, but all constructions that we are aware of are conditional to the ABC conjecture, which is probably not shown yet. So conditional to the ABC conjecture. Now, granted that I can convince you in the course of this talk that such a surface can be constructed, then what can you do with it? One application is we construct a family of Chatelet surfaces say S over P1 such that when we take the fiber product, so S times P1 and then our surface here, such that this has no rational points, but the Brauer-Manin space not empty. Right, so no is simply connected. again, examples of spaces where you have no rational points, but still you have a Brauer-Manin space were known previously, but none of them were simply connected. They were all variations of a construction of beyond Poonen, and these were spaces that were fibered over a curve of general type. So again, I should remark, this might be the first simply connected example over a global field. Where Brauer-Manin does not explain failure of the Hasse principle. Yep.
The application, the x, is that the same as the y in the...
Oh, it is. Yeah. Sorry for that. That should be the y. Right. That, of course, has a very long history. Poonen has these examples fibered over a curve of general type where the Brauer-Manin obstruction fails. But then Skorobogatov has improved the Brauer-Manin obstruction. He now has the etale Brauer-Manin obstruction. And then in Poonen's examples, the etale Brauer-Manin obstruction does the work. However, here our spaces are simply connected, so there's no etale Brauer-Manin obstruction, or at least it doesn't give you anything new. So maybe I should simply say that this has, of course, a long history, and right, I should say first examples by Poonen, and then improvements by Skorobogatov. And one could probably spend a whole lecture series explaining the history of the subject. Here, let me just briefly say how do we find the family of Chatelet surfaces? The answer is, of course, very easy. You get the right co-author. So, remark, I should point out the construction is quite explicit. What do we need to make sure? Need to make sure that the Chatelet surfaces they have no rational points over phi of y of k. That will then guarantee that the fiber product has no rational point at all. And this is doable if you're familiar with Chatelet surfaces. They can be explicitly written down. And if you happen to have done a PhD with Colliot-Hélène, then you know all them by heart. And okay. And then you need to compute the Brauer-Manin space. And this follows basically the thesis of Pereira and Smeets. Thesis of Smeets, while building on work of Colliot-Hélène, Ambrose Paul, Skorobogatov, and Poonen on the other side. Yep.
Can you please just recall what you call Brauer-Manin space?
The space where all the rational points would give you elements. If that space is empty, then you know you have no rational points. And here, we have no rational points, yet we have a space of potential Brauer-Manin classes. Right. So this is basically the application that I have in mind. And now I would like to come to the main point of this talk, namely, okay, this is very nice, but how do you construct the surface here in the first place? This is the essential point in all this. We need the surface. And if you have the surface, then with Chatelet surfaces tricks, which are rather well understood, you can cook up this example. So how to construct a surface Y with a, say, controlled set of rational points. And here we follow some ideas that go back to Frédéric Campana and also a construction of Lydia Stopino. So following Campana, Stopino, find a tower of, well, families of curves. As follows. So we start with P1 over Fp. So the function field of this is our field big K. Inside there, we take a Zariski open subset that needs to be chosen appropriately. Over this, we have the trivial family of curves. This is now, if you wish, a curve over the function field. Call it X, or maybe X naught. And then here comes a more interesting family of curves that needs to be constructed. Family of curves as follows. So maybe this is a great time to draw a little picture, how I think of this. So here's my S naught. Then here I have my X naught. This is now a curve over the function field. And then on top of this, I have a threefold, like so, which is my Y naught, or I can see this as a surface over this function field. This is the construction. We also find a divisor. D naught in the divisor lives on X naught with a few properties. Let me just mention the more important ones. Namely, first, D naught to S naught is etale and 6 to 1. So here's, I have color. Here's some color. Blue maybe. Here's maybe D. Let me just draw one component of D. There's certainly more. We can view X and D over S naught as a family of pointed curves. So fibers are P1, and they have 6 distinguished points. So, and I'm asking that this family is not constant. Better still, I'm asking that the Kodaira-Spencer map does not vanish. So, Kodaira-Spencer map of family of pointed curves does not vanish. And then, maybe most importantly, for our purposes here, I'm asking what the pullback of the divisor is. Namely, this pullback of the divisor, so maybe in the picture, I could just draw it here. It is this side here. This really, I want to be a product. So this is isomorphic to d naught times a 1 connected curve. Actually, it's a tree of rational curves, so this will always be geometrically simply connected, and every component multiple. So this is the setup that we would like to construct, and this can be done. But why is this cool, and why does this even apply to the problem at hand? The observation is this. Okay, this of course will then guarantee that everything is simply connected. But what can we say about the rational points? This is the main thing. So a rational point, a k rational point, k being the function field of S naught, in plain language is nothing but a section like so. And if I have a section like so, I get a curve up here. And then I can take phi of this curve. Maybe the curve should have a color, green maybe. So here's my green curve. I take the image of this curve, and I observe that the image of this curve is not arbitrary, because this blue divisor here that appears with multiplicity. And that forces the image of the green curve to intersect the divisor D here tangentially, maybe to order 3, but certainly not transversally, never transversally. This is what comes out of all components being multiple. So, the central observation. Pardon?
Does this use that you are aware of finite field?
Not yet. Central observation given a k rational point, also known as a section sigma from S naught to Y naught, then phi of sigma of S naught. So intersects D tangentially. So, and if you were bored because you're not interested in problems over finite fields, now it becomes geometric. What I would like to say is, in fancy words, these curves, the green curves that intersect the blue divisor tangentially but never transversally, they are now called integral points. And what I would like to say is that on the surface x naught, together with the divisor d, there's only finitely many integral points. And this is, if you wish, an analog of the classic Mordell theorem for function fields, that surfaces have only finitely many sections. Here, however, with a boundary divisor that prescribes some intersection. So, the crucial point only finitely many sections from S to X have that property. And this is a generalization, if you wish, of the classic Mordell theorem in the function field case. So let me then, still wrong? Uh-oh. I guess we have to use the old-fashioned. Pirate style. All right, so let me make this now a little more precise. So we know what we're proving, or attempting to prove. What I would really like to talk about in this talk is this Mordell theorem and how one can possibly prove something like this. So this is Mordell theorem in the orbifold setting. So let me then specify what the setting is. Now I'll take K, an algebraically closed field. For instance, the algebraic closure of a finite field. I have, this is now better. What did I call this? I call this phi. Phi from x to s, a surface mapping to a curve. So a projective smooth K surface mapping to a projective smooth curve. And then I also want a divisor. D, this is a Q divisor on X, which is of this form with standard coefficients where the mi are natural numbers or perhaps infinity. And I also want an open subset such that the following holds, namely, first, I have the support of D over S naught is etale. So in particular, the components of D are smooth points over the function field. Second, I want that the Kodaira-Spencer map for the family of pointed curves does not vanish. And third, I want that the degree of the relative canonical plus D is positive on the generic fiber. So this is a family of pointed curves of general type. And the divisor here is what Frederic calls a geometric orbifold. It has these standard coefficients. Right. And with this setting, I can now introduce the word of the notion of an integral point. So what is an integral point? It's this thing that we already had. So let me again draw a silly little picture. So we have, here's S, Here's x. This is S naught. We have the blue divisor D. Blue divisor D might look like so. For instance, it's etale away from that point, and an orbifold integral point is a curve C over S, which intersects the blue divisor only with higher multiplicity, where higher multiplicity is, of course, precisely the number mi there. And at this point here, we are really not asking anything. So, an orbifold general point. So this is a S curve T and an S morphism gamma from T to X such that for any index I and for any point over the open set, we have that the multiplicity in T of di is either 0 or mi or mi plus 1 or higher than that. So we are not asking that it's a precise multiple of mi. It could be like 3 when mi is 2. That's an orbifold rational point. And then the main theorem that I would like to talk today, or that I would like to discuss today, is so setting as above. Then for any t only finitely many C integral points. Now I wrote general, it should be integral. And here I should write orbifold to have consistent notation. Okay. Now, how do you prove such a thing? The proof follows the usual pattern. You show that it's the family of all such orbifold integral points is bounded, and then you prove it's also deformation rigid. So, standard procedure. So, prove boundedness, and here in the form of height bounds. And then rigidity. That's the plan. And then after sitting down for a while, one realizes that rigidity in this setup is actually a consequence of height bounds, using some Frobenius cover and deformation tricks. So rigidity follows from height bounds via, say, Frobenius tricks. If you're in positive characteristic and in characteristic 0, you can understand the deformation theory much better, and I'm not getting into there. So really, the interesting thing is the height bound. And that I would like to discuss in more detail. So, what can I say about height bounds? Let me first write down what we have. And if you wish, then all I have told you so far, it was only motivation for the theorem that's coming now, which is perhaps not easily digested if you see it on a sober stomach. So theorem, height bound, and this is really at the core of what we've been doing. So given a positive number, epsilon, all orbi integral points gamma satisfy an inequality of the form height of gamma is at most the maximum of d prime 2 plus epsilon times the discriminant times O of the square root of the height. So where I should say what height is, what d prime is, and what delta is, I think. So where the height is a fancy way of measuring the degree of that curve, namely it's the degree of gamma pullback k x over s plus d, which by assumption is relatively ample, and then divided by the covering degree. So the discriminant is the same thing, but we simply take the canonical bundle of T. We simply take the canonical bundle of T. So delta of gamma is degree, and d prime, this is the degree of kx over s plus d times the GCD of the orbifold coefficients as long as they're finite. So that is really the main result today. Of course, this has a very long history. And there are many names that I should mention, probably including some people here in the audience. Let me just say it has a very long history. And the result that we have here on the blackboard directly generalizes the height bounds that were obtained by Mignon-Kim. So theorem generalizes work of Mignon-Kim. Right. And now I should probably tell you how to prove this result in 15 minutes, which is a bit of a challenge. And obviously I won't be going into the details, which are long and gory. Instead, let me just point out how Kim proves the result without the divisor D, and then I point out what needs to be done. I don't know about your appetite for complicated technical details. Maybe I better give an idea of the work that needs to be done and the entities I think one should be looking into. So how does Kim prove the height bound when there is no D? And he follows the classical path that was pioneered, I think, by Grauer to prove the first Mordell theorem in the function field case, and then improved by Volta. So this is following Kim, Volta, and the very classical paper of Grauer that probably started everything here. Yeah? D prime. So it's the degree of the relative canonical. X is the surface, yeah. So on the generic fiber. Yeah. So it's basically the orbifold genus of the fiber. Thanks. Right. So first, we take N very large, really large, and then the classical Riemann-Roch estimate says that we can find a morphism from the relative canonical taken to the appropriate power into some symmetric power 2 plus epsilon n omega 1x. Right, and this exists, I'm cheating here a little, up to a twist with something ample on the base which will not play a role. Up to twist with ample on S, which I will silently ignore. So, and now, if I have a rational point, so given a morphism gamma from T to X, then I look at, well, the pullback of this sheaf map here. So this is now gamma pullback omega x s tensor n into gamma pullback of the, let me write capital N here, otherwise I have to copy this all the time and I will make mistakes immediately. It's large multiple. And then, of course, I have the differential. I can pull back differentials, get a differential on my curve T, and I can pull back symmetric differentials and then get a tensor differential on T. So this goes to omega T to the appropriate power. Aha. And immediately you see what comes out, namely if this composed morphism is non-zero, then I know that the degree of this thing on the left, which is essentially the height if you look at it, is less than the friend on the right, which is essentially the discriminant. And then there are some factors that make up for this 2 plus epsilon. Blah, 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 blah. Okay, that's the idea. So I immediately get height inequality the T if a composed map is not zero. So the interesting curves are those that Kim calls degenerate. This means that the composed map does get zero. And then what do I do for those? Let me briefly recall that if I have an invertible, say L inside omega 1 of x, I can see this as a foliation, right? So this is a foliation. The composed map, so gamma upper star L, gamma upper star omega 1x, omega t, this vanishes if the curve is tangent to the foliation. So in that easy setting, the Keen's degenerate curves are those that are tangent to a certain foliation. So this vanishes if gamma is tangent to. Okay, and if this was my setup, if I wouldn't have to take these like crazy symmetric products, but simply already have a map at the level of omega 1, then I can say, vanishing, non-vanishing of the Kodera-Spencer map. This tells me that the relative sequence of differentials on the generic fiber is not split. So I can say something about Chern classes there. I can say something about maximal destabilizing sheaf and stability or non-stability of omega 1 on this curve. I have something to say about Chern classes, and then I also get a height estimate. So non-vanishing of Kodaira-Spencer gives info on Chern classes. Great. Then there's stuff that we can do. Unfortunately, we do not have this. What we have is an invertible L in sym n omega 1. So I do not specify at every point a linear function on the tangent space. Instead, I have a homogeneous polynomial. And the solution set of the homogeneous polynomial is, of course, a bunch of lines. So I don't get a foliation. What I get is, I call this a multi-foliation, and then Georges yells at me because this should be called a web. This is a multi-foliation also known as web. And then he politely points out that he has written a book on web geometry and gives me a copy. It always happens. So, and then of course the multifoliations are maybe more difficult to deal with than foliations, and things are not so easy. However, you can turn a multifoliation into a foliation by going to an appropriate cover. So this becomes a foliation after cover. So maybe not so bad. We know something about the Chern classes of this multifoliation. We have non-splitting of exact sequences and a stability. We know something about the maximal destabilizing subsheaf, and then you go to a foliation, and then it matters whether the cover that you take here is separable or inseparable, right? If the cover is separable, then stability remains pretty much unchanged. If the cover is inseparable, then anything can happen. So if cover is separable, then Chern class info stays. If this is inseparable, then too bad. And then you need ad hoc arguments essentially arguing that the kernel of the differential should be treated as a foliation. I'm not going into details here. Let me just say ad hoc arguments without saying precisely what they are. The kernel of the differential for this foliation is something like a foliation that all these curves upstairs will be tangent to. So this is the classic setup, the work of Kim. And then, what do we do in our orbifold case? In the orbifold case, we basically build on ideas of Campana and Poonen. Now I'm running short of time, so instead of writing complicated things on the blackboard, let me just say a few words. So here I have my surface. Here's the blue divisor. Here is maybe the green curve. And what Campana and Poonen tell us, maybe this here appears with multiplicity 1/2, and the divisor is given as y equals 0. What Campana and Poonen tell us that instead of looking at the sheaf of differential forms omega 1, we should look at a slightly larger sheaf, which is generated by these two friends. And then the central observation is that if I pull back such a differential, that has a pole of order 1/2, and my curve here touches with multiplicity 1/2, and I pull it back to the curve, then it will not have any pole at all. And if it touches with multiplicity 3, then certainly no pole. So these orbifold differentials, they pull back to give me honest sections in omega 1, and then the thing up there, number 2, that still works. You get the sequence. However, you got to pay a price, namely that the square root of x is not defined and doesn't exist, right? The square root does not exist, and this differential here does not exist. However, there is a way to make sense of these differentials, not on the surface, but on a cover of it. Here it's a 2-to-1 cover given by the equation t equals x squared. You can make sense of this on the cover. There you get a sheaf, which is commonly known as the Campana-Poonen sheaf of orbifold differentials. And what you need to do is, first, you have to find this cover. Over the complex numbers, people usually take cyclic covers, Kawamata covers, but here we are in characteristic P, and the multiplicity might not be 1/2, but P. So then this is a lengthy exercise in Artin-Schreier-Witt theory to come up with an appropriate cover. And we definitely took the help from Piotr Eichinger there. So find the cover, establish the appropriate Campana-Poonen sheaf, then redo everything that Kim has been done for the Campana-Poonen sheaves, and then, okay, get a height bound upstairs. And then the last thing for the last 2 minutes is maybe the observation that we are the most fond of. So let's look at this little picture here. I take a 2-to-1 cover, and so here I have my blue ramification lockers. I have the green curve that touches to multiplicity 2. This is a 2-to-1 cover. So the green curve will look like so. Now, for the green curve here, we can prove a height bound. And if I look at the height bound, is it still on the, no, it's not. Then the height bound involves the intersection number with the relative canonical. But you have constructed your cover in such a way such that this really works. It multiplies with the degree of the canonical, but then you divide by t over s, so this doesn't change. And then on the other side of the inequality, there is the omega t. Wonderful, because this green curve here, this is t, this is maybe t prime, but not quite, because this is non-normal. We need to normalize, right? So this is not t prime, this is t prime. And t prime here is etale, so that also the degree of omega t compared to omega t prime multiplies with the degree of the cover. This is wonderful, so our inequality lifts, and it's enough to prove it upstairs. Except when you have a curve that intersects to order 3, then this doesn't work anymore. You get a singular curve, and when you normalize, you change the genus. And that goes the wrong way. That screws your inequalities. And maybe the central observation in what we are doing, and we hope to apply this also to some hyperbolicity properties, is that will screw your height bounds. You can't easily apply the orbifold, the analog of the Kim-Voiter-Grauert bound upstairs. You need to observe that the Kim machinery produces better results the more singular the curve is. You can see this already there on the blackboard. It goes to omega t, and it gives you a height bound comparing, well, the left-hand side with the image in omega t, and not omega t itself. And if t is very singular and you normalize, the image gets smaller compared to omega t, so you get better results. And this precisely offsets and makes everything fly. Thank you for your time.